Okay, so today we're going to look at correlation and regression. And first we'll look at correlation. And my little cartoon here, I used to think correlation implied causation, and then I took a statistics class. Now I don't. That's good that the thinking changed. Sounds like the class helped. Well, maybe. Canon for causality from correlation. Okay, so what is a correlation? So I have some data here. Now I capitalize population, and if I'm asking you to calculate a correlation, I should let you know whether it's a population or a sample. The correlation in one form depends on what n you use. And what I have is I have 10 people from the remaining people from the Matchadash diaspora. So the people who live around the world, there's only 10 Matchadash born people living now, and they are all adults between the ages of 30 and 35. So I survey the population and I find out how much they spend weekly on food from grocery stores and other places. And I also found out how much each person spent on restaurant meals. So I did that for the 10 people from this population. And what I want to see is what's the relationship between those two variables. So do people spend a lot on food from a store? Do they spend less in a restaurant? Vice versa. Or if they spend a lot on grocery store food, do they also spend a lot of money in restaurants? So I want to see what the relationship looks like between those two variables. So I'm going to do that. And first thing I can do is I can plot a scatter plot, a bivariate scatter plot. Bivariate meaning I have two variables of interest. Weekly food store spending is the x-axis, and the y-axis is the restaurant expenditures. Each dot represents a person, and if I go straight down from that person's dot, that'll tell me what their food store spending was. And if I go from that dot straight to the left, it'll tell me what their restaurant spending was. And the person I've highlighted here is person 9, who spent $220 on groceries and $150 in restaurant spending. So I need a measure, a descriptive stat, that describes the relationship between the two variables. And I can see here, just visually looking at it, that the more they spend on weekly food, the more they spend in restaurants. So it looks like I have a positive relationship. And it also looks like there's no real, it's delineated in a very nice manner. So it very clearly looks like the more you spend in a food store, the more you spend in a restaurant. So I don't have any cases where someone spent a lot in food stores and spent very little in a restaurant. So all the points kind of like fit on what I could call a straight line. So I could have a best fitting line. If I take the lowest point and I take the highest point and I drew a straight line, it's not necessarily what would happen, but drew a straight line between those 2 points, I would see that the remaining points fit closely on the straight line, defined by anchored by the lowest score and the highest score. So my descriptive stat that describes the relationship has to take two pieces of information into consideration. The direction of the relationship, positive, meaning it goes up, like we have in this situation where the more they spend in food stores, the more they spend in restaurants. I could have a negative relationship. The more they spend in food stores, the less often they go out to restaurants. In that case, it would be the more money spent in food stores, the less time and money they spend in restaurants. And I also want to see what the strength of the relationship has to be in that metric. All the scatter plot points fit on a straight line. That's I'm going to anchor that as a 1 or a negative 1. And that's the maximum. That's the highest and lowest values that a correlation coefficient can have, right? So a perfect linear relationship where the values fit on a straight line perfectly is a correlation of 1 if it's in the positive direction, and it would be negative 1 if that relationship and all the points fit on a straight line is going down. In this case, it would be more money on food stores, less money in restaurants. So my metric is the correlation coefficient, created by Carl Pearson. And as you'll see here, it includes the z-scores. So this is another application of z-scores. And what it is because I have food expenditures and I have restaurant expenditures, a mean 163, mean 104, and two different standard deviations, and that's population standard deviation. What I have to do is I have to convert those two variables into their standardized scores. I convert them to their z-scores. And when I convert them to their z-scores, they're standardized. So now both variables, instead of having different means, both have a mean of 0. And instead of having different standard deviations, now have standard deviations of 1. So they're standardized scores. The correlation is simply the average of the product of the standardized scores. So per person, I take their z-score for food stores, multiply it by their z-score for restaurants. Multiply those two values, do that for all 10 people, and then I simply calculate the average of the product of the z-scores. So it sums up to 9.8801. I divide that by 10, and my correlation coefficient, rounded to 2 decimal places, is 0.99, which means I have a perfect positive correlation, or almost a perfect positive correlation between the two variables. Okay. So it is near perfect, and I can see here, this is referred to as the best fitting line, and all the values hang pretty close to that on that line. A few points scattered below, and that would be the driver of why the correlation is not perfectly +1. So, and that's a perfect positive correlation. Now, we are not in a position to say that those who spend more money on food, that causes them to spend more in restaurants. Could be, we could have had the opposite relationship. I know those who spend lots in food stores spend less in restaurants, but I can't say that there's a causal relationship in that if you spend more on food stores, that causes you to spend more in restaurants, or even vice versa. Okay. What could be the source of the relationship? Well, in this case, the correlation between the two variables is actually driven by a third variable. Each of these people lives in a different country. So person 10 lives in Switzerland, person 1 lives in Tunisia, and these countries on down. Now, the countries where the person spends the least amount of money on average is Tunisia. So the positive correlation between food store spending and restaurant spending is driven by the third variable, how expensive it is to buy food, whether a restaurant or in a store, in the country that the person resides in. So I can't say that there's a causal relationship between how much you spend in a food store and how much you spend in a restaurant. Because in this case, that relationship really is tied to the country within which they reside, and the cost of living and the cost of food within that country. Just to show a positive correlation here, just a couple of examples. If a positive correlation of 1 represents all the points in the scatter plot reside on a straight line. As the points deviate further from fitting on a straight line, the correlation starts to drop from the maximum value of 1 to the point where if there is no relationship and the points are very widely scattered away from a straight line, then the correlation is 0. And in this case, we've got a line that's horizontal. Perfect positive correlation in this case, this is just an example, and this is using a sample calculation. We'll talk about sample calculation in a sec. Negative correlations, same thing, but the line slopes down. And here's calculations for the sample standard deviation for a negative correlation. And once again, now this is a 0 correlation. So you can walk through these calculations on your own and you can do these calculations in Excel. Okay, so just to summarize, I didn't really mention what the sample correlation coefficient calculation is, but here it is. For the population, the population correlation is the sum of the product of the z-scores. So you calculate the z-scores per person and then multiply the two z-scores together, sum them up, and divide by n. So what you're basically looking at is the average of the product of the z-scores. That's when I use the population standard deviation. If I use a sample standard deviation, I'm dividing by n minus 1. It's basically the same calculation. And once again, as we mentioned before, there are computational formulae, and the bottom below is how they used to calculate it relatively cleanly and efficiently if you had to calculate it by hand. Now, once I'll go with the definitional formulae. They make sense. You can do them with small calculations, whereas a computational formula doesn't really explain exactly what you're doing. Okay. You can take some time and we'll walk through this example. The other spreadsheet that I have, I've posted on Blackboard, but we'll take time and we'll calculate. We'll do this in Excel. We'll walk through it together. Okay, you can pause right now if you want to do it on your own. So I want to take that. So I'll enter my data in. Number of cats. Number of dogs. 3, 4, 1, 2, 4, 6. 5, 1, 6, 3, 2. Oopsie. And 0. 3, 4, 1, 2, 4, 6. 5, 1, 6, 3, 2, 0. Okay. I don't like my grid lines. So I need to calculate my mean and my sample SD equal to average equal to and show 2 decimals. And then calculate Z for cats, and I need Z for dogs. Equal to the value minus the mean, and I need to leave it fixed to row 8 divided by the standard deviation, and I'll leave that fixed to the row. Okay, there's my Z-score, 4 decimal places. I can drag that across. The dollar sign made the difference here. So if I show the dollar sign, when I dragged across, it went to C9. Now, when I drag it down, it'll always stay on either B8 and 9 or C8 and 9, because I don't have the dollar sign after the before the number, which means stay fixed on these 2 rows. But if I drag across, you can go with me in some sense for those 2 values. Now, if I've done this correctly, the mean should be 0 and the standard deviation should be 1. Then I want Z cat times by Z dog. This is a sample, so I take the product of the z-scores, multiply them together, and then I sum them. And then n minus 1, because this is a sample, which is, I've got 1, 2, 3, 4, 5, 6, so I divide by 5. The correlation coefficient R is equal to negative 5.87. Okay. Now, there's a very quick way to do this Excel, R in Excel, and I'll show you the formula. Equal to COR correl. I pick my first column of variables, and then I press comma, and then the second array, and I should get negative 0.87, so I get the save value. There we go. So there is a quick way. Now to put the to create a scatter plot. So I want a scatter plot of cats and dogs using charts in Excel. So we want to insert a scatter plot here, and we'll just keep it as a simple scatter plot. And it doesn't really do it justice, and I'll put it as its own move chart, as its own sheet. I'll format. My markers, I want them thicker, and I'll make them dark blue. Oh, I just did the one. Oopsie. There, looking good. Now, you want to see the best fitting line. You can also you insert a chart element. Let's do our titles. So our primary horizontal is number of cats. It's the first one. And then insert a title for the vertical. You use the up and down arrows for the to cursor around. And then just a title. Scatter plot for cats and dogs. Okay, now if I want to see what the best fitting line is, I can add a trend line. I'll just add a linear one, and there we go. And that's the best fitting line. Now back to here, if you want to see what the formulae look like. There we go. Okay, and that is it for correlation in Excel.